Hello and welcome to this re-recording of the lecture on number theory. For some reason, there was no sound on the previous version. So in order to fix this, I have re-recorded it. And as an extra bonus, I have actually improved the slides as well, which honestly were not that informative. So in this lecture, I will talk about modular arithmetic, Chinese remainder theorem, and prime testing. So this basically covers most of Lab 3. So first of all, you're in the first lab, you're supposed to implement modular arithmetic. So basically, the challenge here, or the problem to be solved here, is that you want to count do normal arithmetic, plus, minus, multiplication, so on and so forth. But instead of using integers, we are now using modular, which means that we're in some sense working with equivalence sets of numbers that all share the property that they are the same modulo a number. For example, in this case, it's modular n, which means that we're dealing with all the numbers which are the same when multiplied or added by a factor multiplied by n. So for example, if we're working with modular 3, it means that 1, 4, 7, 10, and so on all are the same. So therefore we can say that Zn is an equivalence relation which contains all these numbers that are the same modulo n. And in your job in lab 3.5 is then to implement plus, minus, multiplication, and so on these. And I mean, doing plus, doing minus, and doing multiplications is very straightforward. The only thing that's a bit less straightforward is the modular inverse. So here we have the question of what does it mean to calculate x divided by y modulo n. And what we can do here is to reformulate it. So instead of dividing, we're multiplying. So what we're doing here is to take x multiplied by the y inverse modulo n. And this is then the same, of course. And this means that what we're looking for is a y inverse such that y multiplied by my y inverse modulo n equals 1. That's the definition of an inverse. And now we can reformulate this as a linear combination. We have y multiplied by my y inverse plus m. And now I realize there is a mistake. It should be n. N times x equals 1. Which can then be solved using Euclidean extended Euclidean algorithm, but only if y and n are relative prime. So basically what you need to do is to implement this. And of course, the observation here is that there only exists a modular inverse if n and y are relative prime, which means, for example, that if y is 2 and n is 4, there is no solution to the inverse. So that's basically the lab on modular arithmetic. Then the next labs are about the Chinese remainder theorem, which is a quite interesting theorem. And it states that if you have r m's that are pairwise relative prime, and that you have r integers, and then now you want to solve a system of congruences, where you have a set of congruences of the form x equals is equivalent to ai modulo mi for each of these r's. And then this theorem states that there is a unique solution modulo m, capital M, which is then the multiplication of all these factors, all the modulus mi's. And that you basically get this by calculating a number yi for each of these equations, which is equals to the inverse of this capital Mi. And this capital Mi is the capital M divided by these factors, basically taking all the other factors except Mi. And then the inverse of that should be equal to yi. And in the previous slide, we saw exactly how to compute this using extended Euclidean algorithm. So in order to solve this Chinese remainder theorem, you basically have to compute each of these yi's using the modular inverse. And this Chinese remainder theorem can also be generalized. Then it's called the generalized Chinese remainder theorem. And in this case, the mi's does not have to be pairwise relative prime. And there are a number of ways of solving this. One way of solving it is to extend it so that, for example, if you have a number that's not pairwise relative, you can factorize it into the prime factors and then add each of these prime factors. And we will actually see an example of that on the next slide. Because here we have an example. So the example here is that we want to find the smallest multiple of 10, which has remainder 2 when divided by 3, and remainder 3 when divided by 7. We can then formulate it as a set of congruences. So we have the two conditions. The remainder should be 2 when divided by 3, and we have the condition that it should have the remainder 3 when divided by 7. And then we should say that it's a multiple of 10. And 10 is not a prime number, so therefore we can split it up into the two prime numbers 2 and 5. And it should, of course, divide both of those. So the remainder should be 0 in both cases. And since 2, 3, 5, and 7 are relative prime, it means that we can now apply the Chinese remainder theorem. And we also know that the unique solution will be modulo 210, which is 10 times 3, that's 30 times 7, 210. And we can now calculate the 4 mi's in the following way. So m2 is 210 divided by 2, which is 105. And the inverse of 105 is modulo 2 is 1. And so on and so forth. And then we can basically plug in these numbers into this here. And we get that solution is 80. So that means that the smallest multiple of 10, which is remainder of 2 when divided by 3, and remainder 3 divided by 7 is 80. And we can check this. So if we divide 80 by 7, we get 77, which means 3 is the remainder. And when we divide by 3, we get 78, and then the remainder is 2. So this is then an example of applying the Chinese remainder theorem. Then we have prime numbers. So that's the last part of lab 3. And of course, you already know that a prime number is any number that's only divisible by 1 and itself. And the first prime and the only even prime is 2. And the first 10 prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. And it can be a bit interesting just to have a sense of how many primes there are in different ranges. So between 1 and 100, there are 25 primes. In the range between 1 and 1000, there are 168 primes. In the first 1000 primes are among the first up to 7,919. And among the first 10,000 numbers, there are 1,229 primes. And the largest prime in assigned 32-bit integers is 2,147,483,647. Such an exciting number. So the first thing we want to do is to test if a number is prime. And that we can basically do, the brute force approach would of course be to check if it's divisible by any number in this range. We can do even better. Of course, we only need to check up to the square root of n, because the square root of n times the square root of n is n. So there's no point in checking any larger number. So now we can get the complexity down to 1 order square root n. Actually, we can improve it even more in the sense that we only need to check if n is divisible by a prime number. The rest of the numbers we can ignore because they are divided by some other prime number. So this is the kind of the best thing we can do. And this was actually invented already in the, I don't know, way back, and the sieve of Eratosthenes. And in order to do this, we're actually looking for something called a prime generator. So, in order to calculate the primes so that we can check if a number is divided by any prime, we need a method for actually generating the primes. And that we can do using a bit set. So we have a bit set of n bits, and we then basically cross out all the multiplications of a prime number. So we start with the lowest number that we know, lowest prime number we know, which is 2. So 0 and 1 are not prime numbers. We take the first uncrossed number, which is 2, and then we remove all the multiples of 2, namely 4, 6, 8, 10, so on and so forth. And then we take the next numbers that's not been selected so far, which is 3. So 3 must then be a prime number. And we then cross out all the multiples of 3, which means 9, 12, 6, 9, 12, and so on. And actually, of course, 6 and 12 are already crossed out because they are even, so they're divided by 2 as well. And then we come to the next, which is 5, because 4 is already crossed out. So that means that 5 is the next lowest prime number. And then we basically continue like this. And then this is called the sieve of Eratosthenes. And it's actually a very efficient way of calculating prime numbers. So here is just some code for doing this. So in this lecture, I've been talking about modular arithmetic, mainly how to compute modular inverse. I talked about the Chinese remainder theorem and also the generalized Chinese remainder theorem. And then I ended by talking about primes and prime testing. Thank you very much. Bye bye.